while playing back the recorded lecture, I noticed that I forgot to talk about the forward and backward substitution that I said I would elaborate a bit for LU decomposition. So how do we utilize our lower triangular and upper triangular matrices in order to conduct forward and backward substitution in order to come up with the solutions to our equations, the AX equals to B problem, right? So let's go to our bamboo paper and see. Okay, it will take a few minutes only. So let's go to the next page. So normally what do? We do LU decomposition. While doing LU decomposition, we take a matrix L and we separate it into its upper and lower triangular matrices, right? But if we say allow row swapping or row exchanges, we need to introduce a new matrix. Okay, that matrix is called our pivot matrix. So we say that okay, now our equation is something like PA is equals to LU, where P is the pivot matrix. So it basically keeps track of all the row exchanges that we perform throughout our LU decomposition process. Okay, so it basically is a permuted version of our identity matrix. Okay, so you don't need to know about the details, just understand how the forward and the backward substitution work. Okay, so if we say when we introduce the pivot matrix over here, this is of course pivot, not the pivot, the pivot matrix, and we switch the color a bit. We say that we have introduced the pivot matrix over here. Now in order to solve our original problem is solving Ax equals to b, right, where we need to come up with a particular column vector x which satisfies this equation right here, right? So we say that we multiply both sides with the pivot matrix p. Okay, we end up with something like this. This is of course another column vector, right? So P, okay. Then we have what? We can say, okay, our PA is equals to LU, right? Because we, whatever original matrix that we have after performing the required row exchanges, whatever matrix that we end up with, which is P times A, we can decompose it to their respective or to their constituent lower triangular and upper triangular matrices. Okay, so what we can do is we can replace PL with LU over here, right? So LU times X vector is equals to P times B vector, right? Fine. So one another step of simplification that we can do is, why not denote the P times V vector as a new vector T. Okay, so we know that P is a matrix and P is a column vector, right? So whatever their multiplication would be will of course be a column vector, right? So if this P is a 3 by 3 matrix, let's say, and this P is a 3 by 1 column vector, their product will of course give me another 3 by 1 column vector, right? So this T vector over here will of course be of the same dimension as the B vector. Okay, let me erase this part. Okay, so now that we have this equation, we can write, okay, let's substitute u times the x vector with a different column vector, with a different variable vector. Let's call it y. Okay, so ly vector is equals to d vector. Now we have a particular y vector which is multiplied with our lower triangular matrix, and we say that we get a d vector as a result. Okay, so we can do one thing over here, which is we can use forward substitution. So I'm not going to talk about forward substitution over here for this course in detail, because I'm assuming you guys have already learned it in your linear algebra course, so you don't need to learn it again for this course. Okay, so with using forward substitution, we'll find out the vector y, okay, that satisfies this equation right here. And after finding the vector y, what we can do is, we know that our upper triangular matrix when multiplied with our x vector gives me my y vector, right? So now that we have solve for the value of y vector using forward substitution. We already know what the vector is, right? So now we can focus on finding our original unknown vector, which is the x vector, by performing backward substitution, right? So when we have an upper triangular matrix, we perform backward substitution, right? So using backward substitution, we find out the value of x. Okay, so after finding out the value of x, what do? We arrive at the solution of ax equals to b, right? So that was our ultimate goal, right? To find out what for what values of x, when the original vector a is multiplied, we get a particular b column vector, right? So this is how we can come up with the solution of a system of linear equations using the LU decomposition method. Okay, we need to introduce a new vector with new matrix, which is the pivot matrix. Okay, and the extra advantage here is that if you have multiple values of b, so let's say if you have many, sorry, so if you have, say, for b you have uh, b1, b2, and so on up to bn. Let's say you have n such b vectors, you don't need to perform Gaussian elimination every time, right? So if you perform LU decomposition once and you keep track of your lower triangular matrix and upper triangular matrix, you're good to go, right? You can just apply forward substitution and backward substitution, and you end up with your unknown column vectors y vector and x vector respectively, right? So that's the advantage, and uh, that's the advantage, or uh, that's the computational upper hand, let's say, that you get for uh, resorting to LU decomposition instead of naive Gaussian elimination. Okay, so yeah, so this was what was remaining from our last lecture. So I have added it, and yeah, this is the end of the lecture in its totality. Okay, Assalamu alaikum wa rahmatullahi wa barakatuh.